Okay, don't have a lot of people on chat. Can make this guy a bit larger. Perfect. And you can see me via this camera, hopefully. Okay, maybe I'll arrange it. Yeah, it's strange. Our computer is working so hard. People, any last moment question about homework 1? Hello. Can you hear me on Zoom? Who's G? Mr. G? Yes, fantastic, thanks. And let me also know if it's lagging too much. And it might be that on Twitch, if you'll go to Twitch along ALG, you'll have the broadcast live and hopefully in better quality. If you see the screen working, it seems very, very yeah. Homework 1, everybody's happy? Everybody? Yeah.
I'm still a little bit confused on 5, but like the harder version of it, not the correction.
Sure, so yeah, the version that I meant to be before the type, obviously. So there are a few questions that all handle the idea of unbounded search. That is, I'm looking for something, I don't know how long it will take until I'll find it. So I can start guessing in various ways. For example, slightly increase the size, increase the size. Essentially, you have the very same thing with the dynamic arrays. That I can each time copy everything, spend a lot of time and gain very little benefit of empty cells that I can fill up later in this array. Or how much should I invest when I swing in a circle? So if we are guesstimating it to be a huge number and we are wrong, then the penalty is quite large. Both in question 5, if I assume that this element that I'm after, x, is way at the end, that k is huge, and that was my guesstimation and I'm way off, then it's a very large penalty. The same goes with dynamic arrays, the same goes with many other questions that I have asked for. So I need to start on a very low note to look for A of k when x, that is index with k, is somewhere very close to the beginning of the array. So I'll have some guesstimate about what is k. This estimate should be quite conservative. I want it to be quite small, but if I'm wrong, and I let you figure out how I know that I'm wrong, then I want to gamble for k, a new k, that will be, of course, larger than this value of k. For example, I can try k plus 1, just the next element, which will just be a linear search. That will take a lot of time. Or I can jump to the middle of the array, but then if I'm wrong, then I'm suddenly in log n world rather than log k world. So the whole wisdom, quote unquote, is how do I pick the next values that I guess so that the penalty, if I'm wrong, is not too large. It's still order k, so I can afford to do various things with this k, and still I don't want to have my next guess very far from this value, but at the same time, I don't want to be incrementally just add something to this value. So somewhere in between, and then the key is, of course, the analysis. In the questions that I wrote and the questions that I didn't write it explicitly, you have to write a proof, no matter what. Anything without a proof will not be accepted. various levels of penalties, but proofs must be there. And it's this opportunity I'm always asked, what is a legit proof and how do I formulate a proof? And I don't have a good question, an excellent answer for it, and I'm not very formal about the proof. I'll quote what my PhD advisor was saying, that a proof is a social process at which one side tries to convince the other side about correctness and try to pretend that something is really rigorous, which is all yes or no, but here will be what I require you from the homework, that a good proof will have a set of bullets, one or more bullets. Every bullet will be a very concise, simple line with not too many in case of this and this, if in case of this and this. Have every bullet very concise, very clear what you want to say in each bullet. And every bullet is either obvious by itself or obvious how a bullet is followed from previous bullets. You need to say, because of item 3, I can now prove the 5th bullet because of something that I said over here in 3. And the movement from one bullet to another bullet should be obvious. Now, obvious is, of course, subjective thing. It's obvious if everybody says that it's obvious. Like, you know it when you see it. But I'm not going to define what is obvious over here. And maybe at this note, quite a few years ago I was teaching, again, algorithms. I required a proof, as usual. I had a student that came to my office and said that here is a proof that he gave, and I said that you're right about everything that you said, but it was an example, it was not a proof. You were required to give a proof, say, for every n, and you gave an example for one specific n. And the answer was that in his country, it was considered a proof, which, knowing this country, he was absolutely wrong, no matter what, but yeah, you got the point. Example is example, it helps you explain to the grader what did you mean, but it doesn't make. You're encouraged to give examples, but don't confuse between them and the proof. Okay, homework 2 that you'll formally get today, but and of course, if you find something that you don't like already, you have the link. You'll get a lot of brownie points toward your class participation. It can help you if you are stuck between A and B or B and C as your final grade. It can help you for recommendation letters. And homework 2 covers a lot of topics, starting from more questions about skip lists via randomized median selection and quicksort, the lectures that I published yesterday that fill up for Monday's meeting, via hashing. So it's quite a few topics. And I'm obsessed about merge sort and quicksort and the randomized selection, mostly because there is so many ideas to pick from it toward other algorithms that it's really general tools that I'm trying to give you to the best of my abilities. It's not because you cannot, if you have to sort a file, what I hope that you'll do is calling a function sort that was optimized to death and not try to do it yourself. That's, I'm not working about quicksort and merge sort as a way to teach you to sort files. Using it as tools because they are general, and each one in its own way are very good examples of divide and conquer in the case of merge sort, and divide and conquer plus the power of randomness in the case of quicksort. Okay, more about hashing. I talked yesterday from home about hashing. People on Zoom, if it starts to be laggy because I see that the computer is really trying hard, let me know. Yeah, you see how what the CPU thinks. And I don't think that I have anything that I don't need. It's, I think that 3 cameras plus the OBS that is one to blame. We talked yesterday about chain hashing, and we talked about 2 examples of hash functions, but when the hash functions are just taking numbers, life are very limited. Most keys that you work with are not numbers, and the power of hashing is that you can hash almost everything as long as you can express it as a vector, as a string, and you just need to do it correctly. And along the way, we're also going to touch today the topic of universal family of hash functions, coming up quite soon. Let's remind everything what is modulo, by the way. Here is my function k modulo 5 that I can think about operation as a plus b mod 5 is just letting a be some point, adding to it b, and of course doing it when you are moving along this circle. And even though you all understand that this is just a modulo part, modulo 5 in this case, then let's keep this figure over here, because we are going to play a lot with modulos today, and it's going to be quite useful. Okay, well, I said many things that you can hash. Most things are at least long strings, and I can always take a long string and make it into a number, but it's, for example, by looking at the ASCII values and somehow make them into digits and just make it a very long number by concatenating all these digits. But you're in troubles because you cannot claim that taking this very long number and multiply by another constant will take linear time. Actually, it might require multiple passes. Not to mention that you need libraries. It doesn't fit one computer world, not 126 bits. You need some unpleasant work about it. And that's one reason to mention this dot product method. Another reason is really because it's excellent introduction to universal family of hash functions. So again, some of the things that I'll discuss today probably know from 345. Other things I think might be new for you. And don't forget, yesterday I talked for a long time about the usefulness of hash function with distributed computing, distributed storage, multiple RAIDs, disks. How do I do load balancing in a fair way between many users that each needs to store some amount of data, but I still want robustness, that the same item of data will be stored by multiple users, and I still want efficient algorithm that will tell me, hey, I'm looking for a piece of data that the users that are possibly having it, I don't want to bug. Users that the hash functions will say you don't need to bug these users. Please check the slides from yesterday. I didn't ask. People on Zoom, any questions for homework 1 before I dive into it? Tell me in the chat. Okay. So, what should I do if I have a string, say B, D, C, Z? Dot product method is telling us, we had, when we worked about hash function. One, the multiplication method said age of k equal a times k, a is some strange constant that we had in mind, takes this number and do modulo m. Modulo m always comes all the time. M is the size of the table. Always m will be the size of the hash table, and age of k was the multiplication method that you probably have seen in 345. Just takes the key and multiply by some strange large constant and do modulo n. That works fine if the key is a small integer by itself. What should I do if the key is a string? Then, as I said, I don't like the idea of multiplying a long string by a number. Instead, I'll pick multiple constants instead of 1a. I'll pick multiple constants, namely a1, a2, a3, and a4, and I'll store these constants with me. Everybody that needs to know about the hash function needs to know what is, in the case of a single constant a, capital A. In the case of multiple constants, needs to know all the ai's, a1, a2, a3, a4, that will be the hash function, and possibly many more constants. And now, what should I do? I'm looking at this string, this vector, B, D, C, Z, part of the text, and I'll take the ASCII value of B, which is 66, multiplied by the first constant A1, plus takes the second constant A2, multiplied by D, the ASCII value of D is 68, and so on. That's just sum up AI times the ASCII value. You got a big number, and then you're doing it modulo n. Okay, and it works very nice in theory. We are going to spend quite some time about this idea of dot product. At the moment, I assume that you have a lot of constants. Practically, you can say I'll just store 10 of them, and after that, I'll do some round robin. Coming back to use A1, A11 will be A1, A12 will be A2, and so on. You could. Okay, but I'll give you already a few rules about how to generate these constants AI. When I had only one key, k, and it was just a single number, it was crucial to pick a really strange and large constant over here. The rules at the dot product are different. How do I generate the constants AI? I don't want them here to be floats. Actually, I want them to be integers, AI. Actually, I'm using the mouse. Sometimes I'll use the mouse because then, no, well, I'm doing, I need to change it on OBS to get screen, and then you'll see the mouse also in Zoom. Okay, so the rule to pick the AI is we like randomness. Pick a random integer not larger than m minus 1, m the size of the table, between 0 or 1. You can pick 0, you can pick 1 as the first constant, and the maximum of AI. Just pick each AI to be a constant. Okay, and the range is quite small, between 0 and m. Now, but on this case, I broke the string into single characters. I can be sometimes more efficient if I think about the string as, let's pick instead pairs of characters at each operation. That is, I picked, I think I was looking for text documents about legal documents. It's something about accounting in when you're buying a new company. So according to section 1223, a non-profit organization, yada yada, maybe it's not company, non-profit. Here is my long string. I want to hash it somehow. I can use the same trick of breaking it into single character, so every key will be, that I break it into, will be just a single character, or I can break it into pairs of characters. Takes the AC, gives them a value. And I'll already tell you how do I call from now on these subkeys. I'll think about the first maybe character, maybe pair of characters, up to you. Let's call the first part of this sub key K0. So K0 will be the first two characters of the key. K0, the first two characters of the key. K1, the next two characters are called CO. That's K1. Of course, give it a numerical value according to the ASCII number. Obviously, K3 will be the next two characters. K4 will be the next two characters, G and blank, and so on until you're done. So now every KI is a pair of characters, and I'll generate the vector. I used all the possible notation of vectors here. I've been using it. I denote A both as a boldface and as an arrow on top to tell you, everybody, that this is a vector. It's not a single number, it's a sequence of numbers. Don't need to think about the geometric, physical. Meaning just think about a vector as a sequence of numbers, A0, A1 that I forgot, all the way up to as long as you need. The AI, as before, each AI is a constant that we pick, random number between 1 and n minus 1. And what will be my hash function? Once again, I'm doing a dot product, basically. Exactly what you know from linear algebra as dot product, that is, you're given two vectors, V, which is alpha, beta, gamma, and U, which is X, Y, Z. Then, as you know, V dot product U is alpha X plus beta Y plus gamma Z. Hopefully you all heard about the dot product. It's also the cosine of something between these two vectors. There's lots of geometry behind it. We don't need it right now. We're just saying AI are the constants that we keep when we are using the hash function. Everybody that can use it needs to know what are the AIs. We pick them before the first item comes. And once a document appears, once these long documents appear, break it into characters. And but now character is two ASCII characters. Everybody's cool. I'm looking at alphabet, where every character of this alphabet is pair of ASCII characters. My new alphabet will start at 0, 0, null, null, and will end analogously at ZZ. Start at AA and ends at ZZ, every pair of characters. It's actually the whole ASCII value. Okay, and just for example, what E will be K0, in this case, the first key is I'll just express this pair of characters as a number in base of ASCII. What base ASCII means, if I think about the number 56, when you think about it in base 10, you think about it as 5 times 10 plus 6 times 10 to the power 0. That's base 10. Base 256 will just means takes the first character you have in ASCII 256, many characters, take A times 256, the ASCII value of A, plus the ASCII value of C, which are these are numbers. And you sum up all these numbers. Notice it's quite convenient to do this hashing, even if it's kind of as streaming or one pass of a very large file, that you have just small chunk of the file in memory at one time, but it doesn't matter. It's one of the reasons that we so much prefer the dot product, is that it just requires us to go through this long document once on memory, and every time that we are reading a few characters, multiply by a new constant, sum them all up, it's likely to be a large number, and do modulo m to get a number that can serve as an index. Clear to everybody what is a dot product? Questions? Zoom? Good. Notice that I wrote here in small that the hash function that takes k. K is this whole long string. K is actually also a vector if you wish, but I wrote here a vector to denote that that's a hash function whose value is determined by the values of the constants AI, A1, A0, A1, A2, A3, and so on. Now let's try to, so far I gave you a few reasons of why you want to use a dot product. It works on very large possible set of inputs, geometric shapes, proteins, drawing, images, frames, text, speech, whatever you want. Just make a pass on it, get numerical value, and multiply each one by a number and sum it up. Very cheap, very efficient. But there is much more math going on in it about why we like the dot product over the other methods. So yesterday I discussed against and in favor about using m is a good or a bad idea to decide that m is a power of 2, say 2 to the I, where I is an integer. M is, say, 10, 24, or m is 10 to the power of I. Is this a good idea or a bad idea? And I said it's very convenient to do operations when m is 2 to the I. It's easier to ask for more memory. If your hash table is full, then that's exactly where you are using the dynamic arrays that we discussed in homework 1. Your hash table is too full, there are too many elements. I'll tell you more what do I mean that it's too full. It's not necessarily that it's literally no room, but it's not enough many empty cells. The load factor that I defined yesterday starts to be too bad. And then you are deciding, hey, you know what, this table 2 is too small, I want a larger table. And usually the operating system, when you are preferring new or alloc of memory, will be happy if you take memory which is of size 2 to the I. It works like, computers like these chunks of memory. On the other hand, there are good reasons to pick the hash table as a number which is not of the type 2 to the I, but actually, from now on, I'll assume that m is a prime number. From now on, m, the size of the table, is going to be a prime number. It's divided only by itself and by 1. And assume that all the keys, k is a big key, and I'll break it into the first character, second one, third one, and so on. I'll actually have a rule. I gave you 2 possibilities. I told you that to start with that you can break it into characters of ASCII characters. Each one has 8 bits. That was the first slide, told you. Each KI has 8 bits, a single character. Then I moved and gave you another option. Each character has 16 bits, 2 characters. Right, 2 ASCII characters was different values of keys. That was in the previous slide. We took the first 2 characters. This one is an ASCII character, this one is an ASCII character. So you can think about it as one number with 16 bits. Binary number with 16 bits, the same for the next one. K1, the same for K2, the same for K3, and so on. You can take maybe 3, you can take maybe 4. How many characters should I have? Well, here is a point to tell you that I'll actually decide about how to slash my file into characters so that every such character, when we think about this character as a number, maybe 8 bits, maybe 16, maybe 32, as a number, it will be between 0 and m-1. And the size of the table. Okay, I will take every ki to be a number between 0 and m-1. So let's stop for a moment, think about how it works algorithmically. You just open a new service for the university. I come to you and said, I'm going to have a bunch of students coming over and I want to store them in your database. And then you'll ask me, how many keys are you going to store? How many students are you expecting? And I'll give you some estimation, n. I'll give you some estimation n, which would be the number of keys that I planned to store. And you'll decide about a number m, which would be a prime. And you'll add to this prime, and it's larger than 2 times n. There's a lot of empty memory here that I deliberately waste. I'll actually keep the table to be at least half empty, and I'll keep the table to be full, to be half empty, and I want its size to be prime. Luckily for us, there is a lot of primes in the world, infinitely to be precise. Right? So we are good in this aspect. And then I can work with this number, and then when you have a key that is coming, then you know how to break it into characters. I mean, it's not very convenient to break them into chunks of 9 bits. It's probably not convenient in terms of indices to have every character of exactly 9 bits. So probably you'll take for either 8 or 16 or 32 is much more, or 64 is much more convenient. Right? Just make sure that every ki will be no larger than m. Okay? And I want to tell you that a lot of wonderful things happen if you make sure to use a hash function in the way that I suggest of the KI. And also, you know what is m. Now you'll pick at random the AI. Each is smaller than m as before. Smaller or equals than m-1 integer, and integers, and voila, you can start. Once the first student comes with a key k, you'll break his name into characters, each one, and character is not necessarily ASCII, but it's as a set of bits, it's not more than m. Okay, and let's start explaining why I'm so obsessed with primes in this case. So let's start with a very simple example. I want to think about the function h of x, which would be a times x modulo m. Let's have a quick example. I'll pick age of x to be 2x modulo 3. 3 is prime, last time I checked. And this constant that I pick, 2 that plays the rules of alpha over here, is a number between 1 and m minus 1. Right? M in this case is of course 3. And we're talking about a very, very small hash table. And I just want to show you what are the possible values of age of x. So I need to compute what is age of 0. I want to compute what is age of 1 and what is age of 2. And age of 3 will be just the same values as age of 0. I made a full circle on my circles. I'm back to 3. So let's do also age of 3 just to make sure. So age of 0 would be what? 2 times x to 0. So it's 0 modulo 3 gives me 0. Age of 1, which is 2 modulo 3, making it 2. And age of 2, 4 modulo 3. 4 mod 3, which is 1. And age of 3, I just made a circle, is 6 modulo 3. How many times when I'm doing my circles? How many times can I do, well, every time I made a full circle, I'm back to 0. And age of 5 will be just, age of 5 will just be age of 1. But I want you to pay attention for some phenomena. When I'm looking at the possible output of this function, the possible output of this function, the inputs will be 0, 1, 2, and the outputs will be 0, 1, and 2. The input was 0, 1, 2, the outputs were 0, 1, and 2. Just some permutation of them. And this little lemma wants to claim that it happens in general, that as long as you are making sure that m is n prime, that's always the case. This type of functions, ax mod m, will take the input and create some permutations, but every element will appear exactly once. Here, every element appeared exactly once, as long as the input was between 0 and 3. And this lemma tells you that for every y between 0 and m, you can find a unique t, value of t, the value of alpha here, such that alpha times t equals what? Equals when? Equals here is math students should screen here that it needs to be 3 horizontal lines instead of 2. It's congruent, it's not exactly equal. Let's just call it equal. It's equal under modulo. This number equals to this number. Maybe I need to add, after I take modulo from both sides. I'm just lazy of writing the modulo on both sides, so I write it only on one side. Okay, so when I write equal modulo m, it means this side modulo m or equal this side modulo m. Formally, it's an equation between groups, but let's not worry. Once again, if I pick any number as an output, once you've told me what is the output that I want, a number between 0 or 1 or 3, and I can alpha I don't have any control about alpha. Alpha is some parameter, some constant that you picked. I don't have any control about this parameter alpha that you picked. That's your hash function, not mine. What do I want to say here? You picked your hash function, you picked alpha. You told me I'm using the multiplication product or the dot product, but only with one constant, just alpha over here, A1 that you have seen in the previous slide. And oh, by the way, the inputs that I'm going to use are only very small set of keys. I only have keys that are between 0 and n, okay? I don't allow you at the moment to take larger keys, only between 0 and n. But what do I want to say? That once I look at your function, age of x, which is ax mod m, for every possible output that you have in mind between 0 and n, there is exactly one input t that I pick, so that if I let your function a times t, this input, I'll get the output that you told me that you want. What does it mean? Here is my copy from yesterday. It has 7 cells. You cannot use cells 8. Prime number. And let's think about the function age of x equal 5x mod 7. So m here is 7. Exactly what you see in the copy. There are 6 cells between 0 and 6. And you are looking at the input, the numbers 0, 1, 2, all the way up to 6. These will be the input keys that you can have. If that's the hash function that you are using, you will not have any collisions. You're saying h1 of the input numbers will go to one of the cells and exactly to one cell. I will not have any collisions and I will not have any empty cells. If you're asking at this point, why do we need to care, it's a very legit question. Wait for it. But at the moment, just see what the implications of what I'm saying. That this function, age of x equal a times x modulo m, where m is prime and x is such a small set of keys, a very, very tiny set of keys, using this hash function, you will never have collisions on this input. You will not have the unique here, means that I don't have two inputs that the function sends both to y. You want y to be cell 6, there will be exactly one item that will be sent to cell 6. There will not be any empty cells. There will not be cells that will, 2 items will be sent to it. Okay. So, and at the moment it's fine if you are saying we really don't care, but there is. So let's try to understand what are we doing with hashing, or data structure in general. And but today I'm teaching you several other applications. And as I'm asking you about it in the homework, but it's very easy to see that if I have the universe, the universe, we talked about it yesterday, the universe are all the possible inputs that I can feed, like all the possible documents that I can feed to my hash table, or all the possible fingerprints, or possible keys. The universe is enormous. Your hash table T going from 0, 1, all the way to n minus 1. N is much, much, much smaller than the universe. What you need from your hash function age is that no matter what key comes from the universe, the hash function should be able to spit an index in the hash table, legit index. The hash table should not crash itself. It's undefined. This is enormous. this is way smaller, implying that no matter how I design my hash function, as long as I don't know what the keys that you're going to send, I will have a lot of keys that creates collisions. As long as I don't know what is the input, you will have plenty of collisions. And most usage of the hash function is that you don't know what's the input. We want a dynamic data structure. Students will come, and every student that comes, you find a place for him or her in the hash table. Can I have, right? You are not going to place the whole universe. You're only going to place the set, capital K, of students that are coming from here, but you don't know what is K ahead of time. When you decide about the hash function, you don't know what is K. So collisions are unavoidable. We cannot really prevent them completely unless we know what is K. If you do know what is K, then theoretically you can find a hash function that is perfect. If you do know what is K, who are the students that are coming, then theoretically you can design a perfect hash function. Practically, it doesn't worth the time. The hash functions that we are describing most of the time are doing great, even if you don't know K and even if there are collisions. We just need to find a way to minimize the number of collisions. My point is that collisions are unavoidable. We just want to minimize their numbers. Okay? And I'm mentioning, if you do know what is K, you can have a way. Look at CLRS. There is, under perfect hash functions, you can find a hash function that will have absolutely no collisions, but then it is useless the moment that one key was added or deleted. And it takes a lot of time to find it, and it doesn't practically buy you anything. Worth mentioning Udi Manber, Google for it. Udi Manber used to be a faculty in our department. He was, I think, from 93, 95, all the way up to 2000. Fantastic algorithmic person. When he left in 2000, they hired John Casasiaglu, Stefan Kobov, and myself, 3 algorithm people to replace this one single Udi Manber. And he left the department because he got an offer to be the chief scientist of Yahoo. And after being the chief scientist of Yahoo, he was, I think, vice president in Amazon for a while. Now he is at Google, chief of algorithmic research, last time I heard. But I think that his financial state is probably secured, but also very, very serious algorithmic person, one of the key people in Google, as I mentioned. And I heard an invited talk that he gave several years ago, and somebody asked him what is the most important data structures that we need to teach our students, and he answered without thinking, hashing. By far. Hashing is the most important data structure that you need to think. And actually he gave another talk where I asked him a few years after that he gave a talk here, and this department came to visit, asking what's the most important, etc. And I asked him if he still stands behind hashing as the most important. He said that, yes, hashing and Bloom filter. That's the other one that's based on hashing that is extremely useful. Bloom filter, maybe we'll have time to chat about. So yeah, we are talking about hashing for a long time because it's so important. Everybody's cool with lemma 1? Understood what you're saying? If I think about h of x as I decided what is a, now it's like something that controls the permutation. Right? It controls the permutation. I insert only the number 0, 1 all the way up to n-1 as input. And my function that I wrote over here, despite that I write over here, and only when my keys are so small, it will create a permutation. We'll send each number to different place. You want a different permutation, pick a different A. A different alpha, sorry. Right? if I replace alpha here will be 1, then age of x is just x. It does absolutely nothing. You saw the example when I used age of x to be 2x modulo 3. Then you saw already some permutation. Okay, anyhow, that's lemma 1. It's not hard to prove it. If you care, you are just saying, assuming that there are 2 of them, and then let's write that if you care, ignore me if you don't want to hear about it. If you are saying that there are 2 inputs, say ax equal a double x both mod m. If I have 2 input x, a x and double x, x prime, which is different than x double prime, then it means that a times x double prime minus x prime equal to m. That's what it means, mod. It equals to 0 mod m. Mod m, how could a number be equal to 0 modulo m? It means that this number equals to, possibly this number is exactly m, because m modulo m is 0. Or possibly it's 0 times m, or possibly it's 2 times m, or 3 times m, because all these numbers are 0 modulo m. So this equals to I is an integer, some integer, times m should be equal to a times x minus x prime. Now let's think about prime decomposition. This number, because both x and x prime are between 0 and m, then this number is smaller than m. This number is smaller than m as well, a. That's how I take a. On the other, think about the prime decomposition, which such number is either a prime by itself or a product of a few other primes. But this number is smaller than prime, this number is smaller than prime. Now I'm somehow, by taking the product of something, I created n, and n is prime, and larger than both these guys. That of course cannot happen. You cannot express 11 as a product of 2 numbers that are smaller than 11. Right? If you got it, fine. If not, not in the syllabus. Okay, so continue with this. The good news, the lemma guarantees that the hash function maps the keys of k, now I'm using capital K as different values, as into different cells of the hash tables with no collisions at all. But of course, that will work only as long as I keep these numbers, my keys, to be so small. If I let the set of keys to be a bit larger, say 3 and 8 both modulo 7, then age of 3 equal age of 8, sorry, modulo 5. Then, because I let the keys be too large. Okay, before moving to the next slide, I want to show you the very same lemma, just on different words. What I did here was that I was obsessed with one hash function. I decided what is A, and I changed the input. Now I'm going to use exactly the same equation, but I think about it slightly differently. I decided about the output, which cell I'm going to map into, and I also decided about the input, one of the keys between 0 and n. So the input is fixed, the output is fixed, both of them between 0 and m. Then the same lemma tells you there is exactly one value of alpha, that is one, if you think about all the different functions in plural. Think about the functions age 1 of x, which is 1 times x mod 5. Age 1 of x is 1 times x mod 5. Age 2 of x, a different hash function, which is 2 times x mod 5, all the way into age 4 of x, which is 4x mod 5. Think about this set of functions, family of functions. What's the difference between these functions? This constant that I wrote here before the x. Lemma 2 wants to tell you that once you decide about which cell you want your output to be and what is the input to the cell, as long as m is prime and as long as both the input and the output are between 1 and n, one of these functions will do the job for you. There is an alpha such that the input, x0 times alpha, modulo n will fall at the output, where you want it to be. We are going to generate not one function, but a family of functions. So all I'm saying right here is that one member of the function will do exactly what you want it to be. We'll take the input from where you want the input to be to where you want the output to be, no matter what the input and the output that you have in mind. Okay, toward the dot product a bit further. Is the font clear? It was stretched with the font. Now think about a set of keys. You probably you have the PDF, by the way. Zoom, you have the PDF on, so it might be harder to read. Now, I'll move from an input to input which is a set of points. I like computational geometry, Amir likes computational geometry. Now my input is a set of points in the plane. Every point in the plane has an x coordinate and y coordinate, xi, yi. The point pi will be assigned by the value xi and yi. And I want to hash these points. I want to store them in a hash table so I can see if a point appears or doesn't appear. And as usual, I'll pick the table size m so that m is larger than 2n, the number of points, and m is 1, as before. And I have my set of points. I want to find a hash function that maps these points to the hash table. But when I had one value k, then I just multiply k, the key, by a, and that was my hash function. That's a 345 hash. Now I have each point that has two fields, the xi and the yi. I can concatenate them, making a very nice and unfriendly number. It's not unique. It has various robustness issues. Or I can use a dot product. What does a dot product mean here? I think that that's the simplest example to understand what the banking thing I want from what's my obsession about the dot product. How do I decide what the hash value of a point? I'll pick now two constants, a1 and a2. I'll just call them alpha and beta here to distinguish. That's just a1 and a2 from the dot product. And I'll compute the xi times alpha plus, I'll take the yi of the very same point, multiplied by the other constant beta. That's just the dot product. First constant that you have in mind times xi for the key pi, for the point pi. Takes the x coordinate, the x part multiplied by the first constant, takes the y coordinate multiplied by the second constant, sum them up, and do this uncontrollable reflex of computing modulo m. And that would be your index. And now let's assume that, and I have various questions where I'm trying to twist your arms to use dot products. And solution that I see a lot of times is let's take the xi and the yi values and then just sum them up together and use this as a hash function. It's a great idea or not. It might work, depending on your data, it might work, it might not work, but it's way too easy to give input that will devastate, sum them up. If all my points are along the diagonal, say the other diagonal, then they all have the same value. Fine, that was 4 points. What happens if I give you text, like documents, books, and I want you to hash it? Does it make sense to sum up all the ASCII values and multiply by a single number instead of multiply each one by a different constant? Yes and no. It might work, but if you have a lot of books, or a lot of frames, say, of an image, then you'll sum up their RGB values. Sure, you'll get, probably for different frames, you'll get different values. But if you look at many, many frames, a lot of them will be quite similar to each other. You'll have the same value will appear many and many times for very different images. And if I have an image, if I have a movie of a person that is walking around the ground, this person moves from here to here between the frames, then I'm not going to think that all these different frames of the movie will have the same ASCII value, but you definitely will not have a huge distribution of them. Many will be similar. In English, once you tell me how many words there are, E is so dominant that you'll get very little variance of how many words there are if you have long text. That's why it's much better to multiply each component by its own constant. So two frames that are separate in anything have a good chance to be mapped to different places. That's why just summing up values, the obvious solution is not regular. Moving along. So I described to you what is the hash function that I'm going to use, pick alpha and pick beta. Alpha and beta will be numbers between 1 and n minus 1. And I'll do the dot product. Now, I'll assume that my points pi are given such that, did I say it here, or if I didn't say that, xi and yi and make sure that both xi and yi for each one of the points is between 0 and m minus 1 and are integers. Don't worry if I said it on the slide, if not, that's it. And that's my hash function. Now, m depends only on the number of points, on n, and what is the universe here? What is the set of all possible points that is taken from? The universe are all the grid of possible points from 0, 0 to m minus 1, m minus 1. Many, many points that can be here. So I'll assume that n is smaller, much smaller than m squared. That is, it's, do I want it? Yes, that n is much smaller than n squared. So the size of the table is m is just roughly 2 times n. And I have m squared many points over here, m squared many candidates points. So there is a good chance that there will be points. Remember, the number of cell values that I generate, the number of cell value that I generate is much smaller than the possible number of points that are appearing. So there is a chance of collisions. There is a good chance of that there will be a collision. But let's try to evaluate what is the chance that I'm going to have a collision. X is between 1 and n, yi is between 1 and n. What is the probability that this hash function that I pick for a point pi will cause the collision, will be indexed to another point pj. If my hash function takes pi and send it to one cell not in the grid, one cell in the hash table. So if my hash function sends pi to this cell, but also sends pj to the same cell, and pi and pj are two different points in my data set. Pi and pj are 2 points in my data set that the hash function sends to the same cell. Age of pi equals age of pj. More math notation and indices that you have seen earlier, at least in this course. Hopefully people are okay with this. Age of pi and age of pj are the same. Both pi and pj send to the same cell. There is a collision. Absolutely could happen. Without intimately knowing what's the input, I don't try to prevent it, but I want to tell you that the chance that it happens is only 1 over n. Chance of what? What do I assume? What is my randomness here? I suddenly talk about probability. What is my randomness here? I don't have any control about the input. Amir had a really bad day and he decided to get even with me, so he designed the worst input for my hash function that he could generate. The one that he thinks that I'll have as many collisions as possible. And Amir knows the algorithm that I'm going to use, but he doesn't know the hash function that I picked yet. If he knows the hash function that I'm going to pick, then he can make much more damage. But if he doesn't know the hash function yet, and I'm not trying to, I'm not doing anything active to protect myself against Amir, but instead I picked the 2 constants at random. Each one, alpha, has the same chance to be 1 or 2 or 3 or all the way to n. The same goes for beta. And they're independent of each other. And now I want to convince you that the chance that there is a collision for any, meditate on 2 input points for my set of points. You decided about pi, you decided what is pj. 2 specific points. What is the chances that the hash function that I pick, of course, I picked this hash function and now I'm stuck with this value of alpha and beta. And by the way, this hash function might be 0, 0, and then I'm really stuck. But alpha and beta could be 0, 0, then it sends everything to 0, and there is a lot of collisions. But generally, if I pick alpha and beta between 1 and m, there might be collisions, but the chances that 2 points will collide, 2 specific points, pi and pj, I meditate on them, is quite small. Understand the rule of the gate. Amir designed the input, didn't tell me yet what are these points. Just told me how many, and now but Amir knows what is the input. At this point, but I don't know the input yet. However, I decided about alpha and beta at random. I picked about them by just tossing points, picking the randomness of 2 values between 1 and n. Yes, Amir told me what is the size of the input, so I decided about, he told me what is n, and I decided about m according to prime larger than 2n. And now I want to say, pick the first point that Amir gave me, and the second point, what is the chances of collision between them? I want to convince you that it's only 1 over n. And that's what I expect everybody to understand. Let's write it down. Let's assume that age of pi and pj were sent to the same place. Age of pi equal age of pj. Which means, remember pi is xi, yi, pj is xj, yj, 2 different points. But since these points are different, then either xi is different than xj, or yi is different than yj, or both. But it cannot be that both xi equal xj and yi equal yj, because then it's the same point. So let's assume that xi and xj are different values. Xi and xj are different values, and I don't assume anything about the yi and yj. Maybe they are the same, maybe. if xi equal xj and yi is yj, then I'm just switching in the whole argument. Okay? So xi is different than xj. However, age of pi equal to age of pj, which means, let's write it in longer form, alpha xi plus beta yj by beta yi mod m equal the same thing for xj yj mod m. Now, as you all know, or should know as CS students, if you write A mod M equals B mod M, then you can also add to both sides -1, for example. Then A -1 mod M equal B -1 mod M, or you can write A minus B mod M equal B minus B, also known as 0 mod M. Right? You can subtract the same value from both sides, and you can multiply both values by an integer from both sides, which is kind of like dividing. Okay, so if I have this equation, then I'll just arrange things differently. I'll take the xi's to the left side. I'll write it as alpha times xi minus xj equal beta yj minus yi, all of this modulo m. And now I'm just applying the lemma that I had in the previous slide. This number on the left side, let's say that I already picked alpha. I picked alpha at random, it exists, here is alpha. And I picked alpha, I'm looking at this number. This is x0 from the previous lemma. What do I have here? I have yi and, no, I want to do it from the other direction. I picked beta. Beta is already a done deal. Yi and yj may be 0, maybe not, maybe identical, maybe not. It is some number. I'll write this number and then I'll call this number capital Y. That's the value of capital Y that you saw in the previous lemma. So I'm like in the middle of the process of picking my hash function. I already picked what is beta, so this value is fixed. What about this value? Xi and xj are not the same number. Xi and xj are not the same number. Let's call the difference between them x0, x0 from the previous lemma. And I still have the chance of picking alpha. What did we say in at the end of the previous slide? That out of all the possible alphas that you can pick, there is only one out of all the m. There is only one such that alpha times x0, what you see here at the bottom, equals y. Out of all the values of alpha that you are going to pick, 1, 2, 3, 4, all the way to m, only one of them will cause this side, this term, to be equal to this term. That is beta picked anywhere you want. To satisfy this equation, you have just one value of alpha that will make this equation. The left side equals to the right side, which means will cause the xi and xj to collide. Now, I don't know about this equation when I picked alpha, but I picked alpha at random. Only one of the possible alphas are bad for me, and all the other values of alpha between 1 and m are all good. Will cause this number to be different modulo m, and this number will mean that the 2 points don't collide. Pi and pj do not collide. I think that it's pretty cool. Now, pick, I don't know anything about Amir. I don't know anything about the input. That's why we are going to call it universal hash function. I don't know, I'm going to generate a set of hash functions so that no matter what is the input, I'm almost surely doing great. Great as if I would just randomly pick the points at random over the hash table. That is, the chance, if I have m cells, let's think about it. Here is my hash table. 0, 1, 2, 3. 4 cells. Not prime, I don't care. I have Pi and Pj. I tossed Pi, it landed somewhere, one of the cells. Now I'm adding Pj. Pj must be in one of the M cells, so if I just toss it at random, the chance of collisions is 1 over M. That's the best you can hope for. You have M cells, Pj was tossed somewhere, what's the chance of a collision? 1 over M. That's the best you can hope for without knowing the input, and that's exactly why universal hash functions are going to appear. So again, the chance that Pi and Pj are colliding is 1 over M. Summarizing it again, the chance that P1 and P2, now I'm calling them P1 and P2, the chance that when I pick alpha and beta at random, the chance that alpha and beta, that Pi and Pj went to the same cell is smaller or equal than 1 over M, which in turns smaller or equal than 1 over 2M. Now, let's think about a set of points in my input. I have N points, and I'm meditating on P1. I'm meditating on P1, and I'm saying out of this set of points that I don't know about yet, Amir knows, I don't. Out of this set of points, what is the expected number of points that will collide with P1? P1 is my favorite. How many other points are there going to be with P1? Depending which values of alpha and beta that I'm going to pick. Maybe I can pick alpha and beta that all of them will be with P1. That's a terrible choice. But I don't know what's going to happen. I pick them at random. So for every values of alpha and beta, I'm asking how many other points ends with P1. Here is P1, it landed somewhere. I pick alpha and beta, and it ended up that P17 is also end up with P1, and so is P30, also with P1. I pick different alpha and beta, and there are other points with P1, or maybe none. Look at this lemma, it's really beautiful. How many points will be together with P1? Here I'm using a little more math that is essentially said that the expected of a sum equal to the sum of expectation. I can say for each individual point, let's see what's the chance that it ends up with P1 and just sum up all these numbers. So for P2, what is the chance of collision? Don't know if you can read it, between P1 and P2. We just said 1 over N. What's the chance that P3 ends up with P1? 1 over N. What's the chance of Pn ends up with P1? The chance when I'm picking alpha and beta at random, of course. What we are saying. What's the chance for how many choices of alpha and beta? Or what's the chance that you pick alpha and beta that will cause Pn to end up with P1, collision between P1, my favorite, and Pn? Chance is also 1 over N. So how many points are there? What's the expected number of points that collide with P1? It's 1 over N plus 1 over N plus 1 over N, all of it for each point of the set of points, not including P1 itself. It's N minus 1 such points in my data set divided by N, but I'm summing up this number N minus 1 times. I'll just call it N to keep it clean. So I have N minus M, but what did we say? I pick M to be twice N. So N over M is smaller than half. So what you all understand now is that the expected number of points that ended up with P1 in the same cell is half. But that sounds very strange. What do I mean? How can it be half? It's either there is a point there or not. How could it be that there is half a point with P1? Help. How could I have half a point with P1 in the cell as expected? The statistic, the professor for statistics, sank the drone in a river with average depth of 3 inches. So how can I have, on average, half a point with P1? Well, remember, I'm making this experiment of picking alpha equal 1 and beta equal 1. Alpha and beta are these numbers that I multiply my function by. But here is alpha and beta that I multiply my function by. It is drawing the arm of the C. When I'm using 1 values of alpha and beta, then I'm getting 2 points, and sometimes I'm getting 1 point, sometimes 5, always P1. If the ever expected number is half, it means that in most of the cases, more than half of the cases, P1 doesn't have a collision with anybody. In more than half of the cases, for alpha and beta, P1 sits alone with no collisions at all. Okay, and the same goes for P2, the same goes for P3, the same goes for each one of the Ps. Does it happen that together or not that I have collisions? I don't know, but almost surely when I'm using this scheme of picking alpha and beta, that is using the dot product, I will have, most keys will have no collisions at all, and the ones that will have with very small numbers. I will not have somebody that is a black sheep that consistently always have a lot of collisions with a lot of other keys. Okay, let's play with this notation a bit more. I started when, so I needed the points where, first because I want to tell you more about geometric data structures that uses hashing, but also because it was convenient to think about the family name and private name, search name and family name, like the XI and YI. That is, each person has 2 names, and that's one way to think about the dot product. What should I do now? But for the whole dot product, we started when we assumed that every Ki was a number between 0 and n. What should I do if it's actually a number between 0 and n squared, for example, or m squared, whichever you want? If it's number between 0 and n squared, then what should you do? Take every key x and express every key Ki and express it as a point. Think about it as a number in base m, as a number in base m. If m is 10, then think about it as a number in base 10, which just takes the first digit. If it's between 0 and m squared or n squared, then it's smaller than 100. It's a number between, say, 0 all the way to 99. That's my Ki. You want to use the dot product, and the proper way to think about the dot product, if m is about 10, m is about 10, and you want to do it properly to enjoy all the benefits, then you say, I look at Ki, say 58, and I'll think about the 5 as my first key, K1, or the X value, and I'll think about the 8 as K2, the second part of the key. And I'll think about 5 times alpha plus 8 times beta. Just broke the 58 into 2 numbers. And the same way you can do it even for Ki, where n is not such a nice number, nice elegant number like 100, but if it's 27, you just think about it as break it into integer times n plus yi, and so on. if your numbers are between 0 and m cubed, then what would I do? I'll express every number as 3 digits. 1, right? Every key, I think about it as a vector where of 3 numbers, xi, yi, and zi. And you can always express this number in this way as a x, such that ki is xi plus yi times m plus zi times m squared. If it was larger numbers, then I had something times m cubes, then I had m to the 4th, m to the 5th, etc. That's just a very convoluted way to say, think about the different characters. You started when you think about, 3 more seconds. You think about k is a key as a list of a lot of bits. And your algorithm, and the dot product also only said, takes the first character so that this as a binary number is smaller than m. This as a number is smaller than m, this as a number is smaller than m, and so on as binary numbers. And practically you'll probably want to take it as either 8 bits or 16 bits or 32 bits for each character. Multiply each one by a constant, alpha, beta, gamma, alpha 1, alpha 2, alpha 3, A1, A2, A3, etc. And well, that's will work fine. And should I mention that this is, okay, it will wait for, okay, I'll have to remove this question because you have a question about universal family of hash functions. So what essentially we created is, by managing all the alpha and beta, we created not one hash function, but a whole series of different hash functions. It's a family of hash functions, H1, H2, H3, etc. What the good thing that happens to us is that if we are doing the dot product, then this family is universal. What is universal? It means pick any 2 keys that Amir gave you, wants to, 2 different keys, and ask, out of all these hash functions that you can use, what's the chances that you picked one that is really bad for K1 and K2? What's the chances that they fall into the same place? 1 over n. What's the chances that you pick a hash function that causes them to collide? 1 over n. For any 2 different keys. If it works, then you call this function a universal family of hash functions, if it satisfies this condition. And the dot product satisfies it if you are doing all the rows, because that's exactly what we proved today. So probably it was the most mathy class in this semester. Hopefully it was not too bad. Please finish reading what is in this slide. There is nothing more that you cannot understand, and so you can answer the whole part. And on Monday we'll talk about open addressing. You might have seen it in 3:45. There I would not say a lot of things. It will take me about half an hour. Continue, maybe depending on you, we'll do a bit, try to solve a few problems together if you'd like. I'll also make a little of Piazza, ask how many of you want to participate in this way. And if Monday is a good day for it, or wait for next Wednesday. Questions, people? Okay. Thanks, everybody. Bye.